Hello, I'm Xi. I'm happy to present our work, Generalized Probability Selection and Testing with High Confidence, which is a joint work with Edith, Jelani, Tamás, and Uri. So this paper is a paper about differential privacy. Let's start by giving a quick review of the definition. So differential privacy is a mathematical framework for protecting individual privacy in computation. So formally speaking, fixed two parameters, epsilon and delta, and randomized algorithm A is called epsilon comma delta differentially private if for any two adjacent data sets D and D prime that differ on only one item X and a set E, it holds that the probability that A of D lies in the set E is multiplicatively close to the probability that A of D prime is in the set E up to an additive failure probability of delta. So intuitively, it tells you that whether X participates in the computation or not has little impact on the result. And in this way, the privacy of the individual X is protected. So generally speaking, smaller epsilon and delta are better for privacy. And roughly speaking, we can interpret this definition as saying, with the probability 1 minus delta, the algorithm is epsilon private. Now, here is an outline for the rest of the talk. We will first state the background, the problems we are interested in solving, and our results, our progress towards solving the problems. So this part is further split into two subsections, private selection and private testing. In the second part of our talk, we would like to mention a technical highlight of our paper, which is a method for boosting confidence for private testing and a sparse vector technique. And then I will conclude the talk. Let's move on into the first part of our paper, the private selection. Here, the background is that we are interested in solving a task pi with our private data D in a private manner. And for this task, let's say we have k different candidate algorithms, A sub 1 up to A sub k. Each of them satisfies privacy epsilon 0 dp. However, for our private data D, we don't know which one is the best one for solving the task on our data. And we want to find out and use the best one to achieve the best possible utility. The most naive attempt would be running each algorithm once and then finding and outputting the best one. However, if you analyze the privacy of this total algorithm, you can think of it as a composition of k independent running epsilon comma 0 dp algorithms. The privacy bound simply degrades to k epsilon comma 0 dp, or epsilon times square root k comma delta dp if you use the so-called advanced composition theorem. So this is a very pessimistic analysis. It allows you to publish all of your k outcomes for running the k algorithms. But however, in our scenario, we are interested in only in the best algorithm and the best outcome. Can we do better? Before stating our results, let me mention two prior works. First, in Stock 2019, Liu and Tawa showed a remarkable result, which is the first private selection algorithm that selects from an arbitrary number of private candidates. The selection algorithm has a reasonably good utility guarantee. It satisfies 3 epsilon comma 0 dp. So the privacy degradation is a factor of 3, which is independent of the number of candidates. They also considered improving the constant 3 further and come up with 2 plus little o1 overhead version of their algorithm. But the analysis and the algorithm get much more advanced, and they can only achieve approximate DP, meaning a DP bound with a strictly positive delta. Here, the main idea of their algorithm is to run each candidate for a random number of times and then select the best outcome. So by randomizing the number of executions of each base algorithm, the privacy is somewhat protected magically. The beautiful subsequent work by Peppernot and Stank presented yet another selection algorithm satisfying 2 plus little o1 epsilon comma 0 dp for any desired alpha. So they can achieve this 2 plus little o1 epsilon dp guarantee with a substantially simpler algorithm. And they also put forward a framework for analyzing private selection under the Renyi DP framework, which is very nice. Now we are ready to introduce our results. So in this paper, we come up with a general framework for doing private selection and testing. When apply our framework to the private selection part, we get a private algorithm that selects from k private candidates and satisfies 2 plus little o1 epsilon comma 0 dp. And compared with the Liu-Tower algorithm, our algorithm has the same advantage as the Paper-Knox-Stank algorithm, namely it is faster and it always achieves pure DP as long as we start from pure DP-based algorithms. And comparing with the Paper-Knox-Stank algorithm, our algorithm achieves the same constant factor, meaning that the 2 plus little o1. However, algorithm has an additional advantage of being easier to prove. So in particular, our analysis doesn't need to go through the rainy DP calculation. And I would also like to mention that it is proved by Liu and Tower that overload of 2 in the privacy degradation is optimal if you want to select from many DP candidates. So in that sense, the Liu-Tower algorithm, Paper-Knox-Stank algorithm, and our algorithm are essentially optimal in terms of the privacy overhead. As our second set of results, we observed that we can use the private selection framework to boost the confidence bound for many basic data analysis tasks. So this is kind of a simple observation, but in our opinion, it's very useful because the original motivation for doing private selection is to do hyperparameter tuning in private machine learning. And yet we observe that this private selection framework is powerful enough so that for many basic data analysis tasks, we can use it to improve the confidence bound for given algorithms easily. Maybe a representative example is the problem of releasing counting queries. So let's see the application now. Let's describe the problem first. Here, we are given a set S of population, and we want to privately answer C counting queries. For example, the set S can be all the people live in a particular area, and we are interested in a bunch of counting queries. Each query is over the form, how many people in your set satisfies the statement P. Okay, so this is the counting query. And understanding the utility privacy trade-off for this problem is kind of a fundamental question of DP and has been studied extensively over the past decade. So here by this trade-off, I mean, we fix a privacy bound epsilon and delta, and we want to ask what's the best accuracy we can achieve in answering these queries. And in terms of approximate DP, the following 2 results are somewhat the state-of-the-art results. So the first one is by Ghazi, Kumar, and Malurangsi, which shows that for any epsilon delta, they came up with an algorithm satisfying epsilon comma delta DP such that with high probability answers all of the C questions accurately. Here, quantitatively, by accurate, I mean their algorithm outputs a quantity that is additively close to the ground truth by an additive error of at most 1 over epsilon times square root C times log 1 over delta. This additive error term is known to be optimal, namely there is a matching lower bound. A concurrent work by Dagan and Kuo shows that for any epsilon delta such that as long as there is a mild restriction on the delta parameter, they can come up with an epsilon comma delta DP algorithm such that with probability 1 answers all of the C questions accurately. So having a with probability 1 guarantee is desired in some cases, and the GKM algorithm as itself cannot achieve this. On the other hand, the GKM algorithm works for the 4-parameter regime of delta, whereas the Dagan core algorithm only works with lower bound on delta. And here we observe that if we use the private selection framework on top of the GKM algorithm, we can kind of achieve best of both worlds. Namely, for any epsilon delta parameter we are interested, we can answer all the questions accurately with probability 1. So that's our results for query releasing. And that's all I want to say about private selection. Let's move on to the private testing part. Here we have an even more interesting background. Let's say suppose you have a claim P about your private data D. For example, the claim can be that the majority of the individuals in the data set satisfies a given claim. Now, you would like to design a private test to verify the truthfulness of P. And also you want to only pay the privacy loss only if P is not satisfied. This requirement is kind of intuitive and natural, because if the claim is indeed satisfied, it would not be a surprise to you. Because you come up with the claim, you don't need learn anything new from this verification. And only P being false is kind of very surprising to you and tells you substantially something new about the data set. So in the literature, there is a classical example of this abstract task, namely the sparse vector technique, which can be used to verify claims of the form f of a data set is less than a threshold for one Lipschitz function f. Here, being one Lipschitz, I just mean that if I change any single entry in my data set, the f value of the data set changes by at most 1. Okay, so the sparse vector technique can be used to verify claims of the form, and we pay the privacy loss only if the outcome is above the threshold. If the outcome is below the threshold, we pass the query without apparently paying the privacy loss. So potentially, one can use sparse vector technique to answer an unbounded number of queries. So before stating our results, let's also mention the previous work. In this beautiful work by Liu and Tower, we have already considered generalizing the sparse vector technique to handle arbitrary private verifiers. So here, to model an abstract or an arbitrary private verifier and private claim, let H be a private algorithm with binary outcome, which we think of it as a verifier for the claim. So its outcome is either accept or reject. And given such a private verifier, Liu and Tower designed an algorithm to simulate H of D that satisfies two properties. So first, their simulation is kind of useful, meaning that if H of my data set outputs accept or reject with the probability very close to 1, then it means my data set is extremely satisfied with the probability or extremely unsatisfied. And since the outcome is kind of determined, the simulation needs also output accept or reject with high probability in order for it to be useful or to be faithful. So this is a utility requirement. And in terms of privacy, we would like to have the property that the simulation only incurs a privacy loss only when the outcome is reject. As we have said, if the outcome is accept, it's kind of not considered a surprise to the data analyst, and we don't want to pay privacy cost in that case. This is very nice. However, there are some limitations with their algorithm. So first of all, in general, this simulation does not offer pure DP, even if you start with a pure DP verifier H. So namely, they ended up with a privacy bound with strictly positive delta. And another drawback of their algorithm might be that the algorithm has a high running time. In order to run their simulation, they need to run the given verifier H for many times and do some highly involved post-processing, which makes their proof very complicated. We are ready to introduce our results. So when applying our framework to the private testing scenario, we can get a new algorithm that privately simulates the verifier H. Here, we kind of achieve a similar utility privacy trade-off as the LT algorithm. Namely, when the H of D outputs accept or reject with probability close to 1, our simulation is also to output that verdict. And our simulation only incurs a privacy loss when the outcome is reject. Our algorithm has the additional advantage of being always pure DP, as long as we started with pure DP-based algorithms. And our algorithm has a simpler description and analysis. And in the third set of our results, which is the technically most interesting part of our contribution, we propose a method to boost the confidence of private testing. And our method is especially advantageous when there are a large number of learning tasks. And as an application, we are able to improve the dependence on the confidence parameter in private multiplicative weights updates and adaptive data analysis. So in these two applications, the sparse vector, the standard sparse vector plays a key role. It is a key component in these two applications and their underlying algorithms. And since we are using probability testing to generalize and ultimately improving the sparse vector technique, it is no surprise that we are able to improve these two algorithms. Okay, let me highlight one technical innovation of our paper, which is a method for boosting confidence for private testing. And we will use the sparse vector technique for illustration in this talk. Okay, this is our main result 3. So in one sentence, our contribution is to find a new method to boost confidence by repetition. And here in more detail, let's start by reviewing the standard sparse vector technique. Here, given a query fi and the threshold t, the sparse vector technique wants to verify if fi of the dataset is less than the threshold t. To do that, the standard SVT adds a noise to the fi value. So consider fi of d plus a Laplace noise with magnitude roughly 1 over epsilon. So if I plus noise is less than the threshold, then what can we say about fi of d? Well, at least we can say that with probability 1 minus delta, fi of d is upper bounded by t plus 1 minus epsilon times log 1 over delta. Similarly, if fi plus noise is greater than the threshold, then at least we can say that with probability 1 minus delta, we are confident that fi is lower bounded by t minus 1 over epsilon times log 1 over delta. And here, this 1 over epsilon times log 1 over delta term is considered the additive error of the sparse vector technique. And you can notice that this term scales linearly with log 1 over delta. And here we ask the question, can we do better? It turns out we can in a particular parameter regime. So let me state our algorithm. Given the query fi and t, let's consider run the test fi plus noise against t independently for log 1 over delta many rounds. So let's consider the outcome of these tests. If all the tests returns less than, then we are at least 1 minus delta confident that fi of d is less than t. This is just because if fi is greater than t, then we fail each test with probability at least 1/2, and it's very unlikely that we fail none of these tests. So in this case, so if all the tests returns less than, we kind of get the conclusion that fi of d is less than the threshold t without apparently paying any privacy loss, because in the standard SVT, you incur a privacy loss only if the outcome is greater than. However, what if one of the tests returns greater than? In that case, we are not so confident that fi of d is greater than t, because especially when delta is extremely small, then log 1 over delta is large. We repeat this test for many. When we repeat the test for many times, we are getting more likely to see the result that fi plus noise is greater than t. Still, we might hope that fi of d is at least lower bounded by t minus quantity. That's what we would like to verify in the next step. So if we happen to enter the second case, then we consider comparing fi with t minus delta for some parameter delta we are going to set later. So to verify this inequality, we consider comparing fi plus noise versus t minus delta for another log 1 over delta rounds. And here the similar reasoning goes. So if all the tests returns greater than, we are at least 1 minus delta confident that fi is at least t minus delta. And here, similarly, we get the verdict without paying privacy loss. However, if one of the tests returns less than, we are not very confident that fi is less than t minus delta. But still, we can switch back to test if fi is at least upper bounded by t. And in general, our algorithm alternate between testing fi is less than t and fi is greater than t minus delta. We alternate testing these two claims until we pass one of them. And so to make this work, there are many technical details we need to fill in. But here, are two most significant issues that I would like to highlight. And I hope to, by explaining these two issues, I hope to convince you that our approach is a plausible one. So the first issue is how to control the privacy loss in our algorithm. So recall that in the sparse vector technique, each time you get a above threshold result, you need to pay the privacy loss. And in our context, each time we switch to run another test, we need to pay the privacy loss. And in our algorithm, recall that we are alternating between fi less than something and fi greater than something. We are alternating between these two tests back and forth. And it might happen that we will just waste our privacy budget by alternating these two tests without getting a useful conclusion. So how to avoid these bad cases? Well, it turns out by setting this parameter delta to be reasonably large, we can show that this event happens rarely. So in particular, so if we are interested in answer a total number of m queries, it suffices to set delta to be 1 over epsilon times log m plus log of our delta. And in that case, we can show that we are indeed using the vast majority of our privacy budget to answer meaningful queries. We are not wasting our privacy budget to doing this back and forth thing. And here also intuitively, delta is the additive error of our algorithm. Namely, by using our algorithm, we are able to distinguish between the case that fi is less than t minus delta from the case that fi is greater than t. But if fi lies in between t minus delta and t, our algorithm can output both outcomes. And in that case, we think both outcomes as being valid. The second issue is that in the standard SVT, one also needs to add noise to the threshold t. And so one can think that if the noise added to the threshold is already large enough, then it does not make much sense to do this back and forth testing. So to resolve this issue, we observe that there is a version of a sparse vector that only adds noise to the threshold once. And adding noise to the threshold once is not impressive. The more impressive thing is that by adding noise to the threshold only once, you can add a much smaller noise to achieve privacy. And it is exactly the much smaller noise that allows us to improve on the applications that we'll mention soon. So that's two issues I would like to highlight. And this technique, this sketch skips many details in our implementation of this idea. And if you are interested, I encourage you to see our paper for more details. Let me mention the application to private multiplicative weight update and adaptive data analysis. So for private multiplicative weight update, the setup is that, so first of all, this is a private implementation of the multiplicative weight update algorithm. The setup is that we are given n samples from a finite universe, and then we can answer m linear queries with these samples within arrow alpha, where the alpha grows only logarithmically with the number of queries. And this algorithm achieves different privacy guarantee and reasonably high confidence. And when applying these private multiplicative weight updates to adaptive data analysis, we can answer m adaptively chosen linear queries within arrow alpha and confidence 1 minus beta. And the sample complexity grows logarithmically with the number of queries. Using our new sparse vector technique, we are able to further improve the error and the sample complexity. In particular, the new bound looks like the following. So basically, everything else remains unchanged, but we are able to decouple the dependence on log 1 beta from that on other factors. And we kind of achieved the optimal dependence on log 1 beta. And this is the main message of our improvement. Let me wrap up. So in this work, we following two beautiful prior works, we propose yet a new method for conducting private selection and testing. Our method offers similar or sometimes better privacy utility trade-off as prior works, but our analysis is significantly simpler. And in some sense, our paper generalized sparse vector and exponential mechanism, not only the application and algorithm, but also the proof. We further extended these frameworks in two directions. In one direction, we showcase how to use private selection to boost the confidence bound for popular private data analysis tasks. And in the second direction, we show that how to boost confidence for the private testing framework in the online setting. And as a result, we are able to improve the sample complexity dependence on the confidence parameter in private multiplicative weight updates and adaptive data analysis. That's all I want to say today. Thank you for your attention.